Okay, so 4.3 in your Calculus 30 textbook here on page 178. We're going to talk about the first derivative test today. First derivative test. Now, what is it testing? Well, let's talk about a function that we have done sign analysis on to find where the function is increasing and decreasing. You will remember this example from previous class. If this is our function, this is the derivative of that function. We then factored the function and performed sign analysis. So you don't really have to copy this down because you should have it in your notes already. So just listen to this part. The sign analysis has showed us what? It has given us the sign, S-I-G-N, of the derivative. And we see that in this interval, right, from negative infinity to negative 1, we found out that the function, f of x, right, f of x is decreasing. And on other intervals, f of x is increasing. All right? And what we did was we then found our critical numbers. We placed them on a graph, negative 1, 0, and 4. And negative 1 be about here, 0 is here, and 4 is over here. Right? And what we've learned is that where there are relative or local maximum and minimums, we are going to have some kind of critical number. And that critical number is the x value that makes the derivative 0. So you see at all of these three numbers, the derivative is 0. Okay? So this is all a review here so far. We then graphed it, right? And we said, okay, at negative 1, we have a derivative of 0. That makes sense. And we also said that the slopes of all the tangents between negative infinity and negative 1 are negative. So we see that we have the slopes here. They're all negative, right? They all go down from left to right. And you should remember this, right? Is this ringing any bells? Yeah? Okay. And then between negative 1 and 0, all the slopes are positive. Right? So I want to just kind of focus on this here for now. There's these two areas. I know this is kind of small, but when we have the slopes of the tangent lines being negative over an interval, and then switching to positive for a continuous function, a polynomial function, what we have is we have a local what? What is this again? It's a local minimum, okay? Because as we look at all this, if we look at the graph right around that, you know, if this is the kind of the blow up of that graph, right? It's a local minimum. So the first derivative test basically just formalizes what we've already learned about the sign analysis of a derivative. And that is when the sign of the derivative changes from negative to positive, that is negative slopes, and then changing to positive slopes, that at this critical number, this indicates that we have a local minimum. When the slope changes from negative through 0 to positive, like at number 4, we have the same thing, right? Negative through 0 to positive, a local min. What about when the slope changes from positive through 0 to negative? What do we have? We have a local maximum, like right here. So that's what the first derivative test basically says, is that if the sign of the derivative changes from negative to positive, we have a local minimum at that critical number. And vice versa, when the derivative changes from positive through 0 to negative, we have a local maximum at that point. That's called the first derivative test. So I'll let you just copy that out here. I'll just put it up on the screen. The first derivative test. So when the derivative changes sign from positive to negative at a critical number c, then the function f has a local maximum at that c. So think about positive positive, positive to 0, critical number, that's what makes it a critical number, 0. Then it goes to negative, negative, negative. That is a local maximum. See that? Consequently there, when the derivative changes from negative to positive at a critical number, then the function has a local minimum at that critical number. And if we think about, negative, 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 at a c we have a 0 value for derivative. Then it changes to positive, positive, positive. Well, it makes sense that this is, for the graph, a local minimum. If we see that the derivative, okay, and remember we're doing all of this examination on the derivative, not on the function itself, but on the derivative. That's why it's called the first derivative test. This is the first derivative. If the sign doesn't change at c, then we have no maximum or minimum there at c. And when would that be? Well, let's say we have positive, 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 0, but then after the 0 we still have more positive, positive slopes. See that? And what does that look like? That looks like this graph right here. Maybe a cubic function. See that? No, there is a critical number because at this exact point right here, at one point the derivative would be 0. Yeah, the derivative would be 0. But it does not change. Okay? So if we did something, now this isn't a cusp, right? Remember the cusp doesn't exist. But if we did, let's say x cubed, right? Y equals x cubed, okay? That's what this looks like right here, y equals x cubed. So if we did sign analysis, and we did the derivative, 3x squared, and we did sign analysis on 3x squared, right? We could factor that if we want into 3x and x, that's fine. So let's factor it, let's do this. We do sign analysis, x is 0 at 0, and it's negative before that, it's positive after that. 3x is 0 at 0 as well. It's negative before that, it's positive after. So what we have is we have the derivative then is positive here, it's 0 here, and it's positive afterwards. So that's what I mean. That's saying, that's the third point right there. It's positive, goes through 0, and it's positive again. It does not change sign. If it doesn't change sign, if it goes either way, negative, 0, negative, or positive, 0, positive, then there is no relative maximum or minimum there. So no relative or local max or min. Okay, does that make sense there? It's a good point. I'm glad you brought that up. But that's what that means. That's what point 3 means. And yes, there is a derivative of 0 here at one single point. I don't know if you guys remember pre-calculus 30. Do you remember describing this shape of graph? We said that it comes tangent to but crosses. Tangent to and crosses. That's the behavior at that 0. When we talked about multiplicity of factors, if you guys remember that. But coming tangent to means that it at one point it comes exactly tangent to. It has a slope. Tangent line would be 0. Any other questions about that first derivative test? All right, so if we only had the sign analysis and we only had the sign of the derivative and not the graph, okay, like for example right here, we did this the other day, but without looking at the graph, the derivative here is positive, and then it's 0, and then it's negative. What do I have at negative 3? Yeah, if you want, you can draw positive slope, then draw a 0 slope, then draw a negative slope. So what are you creating? You're creating this. So that's a local max. And over here, it's negative, and over here, it's positive, and here it's 0. So going from negative to positive, what do we got? A local min. That's what the first derivative test is. Now, you probably could have come up with that on yourself, by yourself. Like, what's the rule for how the signs change? What do you have? What does it give you? You might have come up with that on your own. All right, but we've already basically come infinitely close to this law anyways. So I'll just give it to you. Okay? Any questions? Okay. All right. Take a look at the chart on page 179. That's right here. And this is an example here of what I'm talking about, right? This is to the left of C, the derivative is positive. To the right, it's negative, so that's a local max. To the left of C, the sign of the derivative is negative, then it's positive, that's a local minimum. If the sign does not change, like in the last two examples you see at C there, we do not have a local maximum. So in some situations, we can see that you can test for absolute values as well. And that would come in this case. Let's say you only have one critical number. All right, so I'm just doing kind of a mock. So here's a factor, and there's only one critical number, okay, at C. And if the derivative is negative here, it's 0 here, and then positive here, and there's no other critical numbers, there's no other sign changes in the derivative, then let's see, this is negative, this is positive. So it looks like we have some kind of parabola here, right? And so there's no indication that the sign changes. So all of these tangents are positive over here, all of them are negative over here. So this, in this case, you could say, hey, this is a local minimum, but it's also the absolute minimum because it's the only one. Right? So in this case, you could say f of C is absolute minimum. Okay, so 3e on 4.2 was asked about, so I'm just going to do that question here. 3e. 3e looks like this. Y equals 2x cubed plus 3x squared minus 6x plus 3. All right? And we're asked to find the critical numbers. Okay, so let's find the derivative. Y prime is 6x squared, right? Plus 6x minus 6, right? Take out a 6, we've got x squared plus x minus 1. All right. Now, the trouble you may run into here is factoring this, right? Okay. So does it look like you'd be able to factor it sort of like the traditional way, x times x? You know, what are the factors of 1, negative 1 that add to positive 1? No. Okay. So this is where you run into troubles, right? All right. So we can't do it this way. Do you remember another formula that you might be able to use? The division formula? Yeah. Well, x equals negative b plus or minus root b squared minus 4ac all over 2a. Wow. Yes. Jack in the box, okay? So this helps us find the roots for a function. Now some functions maybe wouldn't have, like some quadratic functions wouldn't have roots, right? If you have a function that looks like this, no real roots, so you're not going to have an answer. What you could do to check, and this is called the discriminant, you can actually check this first, because this has to be 0 or positive. If this value right here is negative, you got issues, and there are no roots for this, and so there wouldn't be any critical values, I guess, or critical numbers. So let's see, b squared, b is 1, so that's 1 minus 4 times 1 times a negative 1. So that's 1 plus 4. So it looks like we're going to be okay. So we are going to have an actual value. So you'll go x equals negative b, which is 1, plus or minus the square root of 5, all over 2. And so your x values that make this, right here, this thing, to make this 0, would be negative 1 plus root 5 over 2. And positive 1, negative 1 minus root 5 over 2. And so these would be your critical numbers. Yeah, but you have to use the quadratic formula. So those are critical numbers.